Hello, I'm Micah Pedrick. I'm the other TA for this course, and I'll be the one doing the section recordings for these last few weeks in the quarter. So the first section that I'm going to talk about is the sort of basics of double integrals, doing integrals over area rather than the sort of one-dimensional line integrals that we were talking about earlier. So the first and simplest thing going on is talking about these rectangular domains, where there's no dependence between x and y. There's just an interval in x and an interval in y. They're giving us this rectangle in R2. Our function's defined there. It's integrable, which will usually just follow from continuity here. And our sort of main practical result is this thing that's sort of called out in the end of the 16 February and the beginning of the 18 February note from lecture, is this idea that we can carry out this sort of abstract integration that's sort of over these little rectangular chunks and do it by just sort of iterating single variable integrals, either first in y and then in x, or first in x and then in y. And the choice of order between the two can make a problem easier or harder sometimes. And so it's a good idea to sort of think carefully of which one to go for. So as an example here, I've got this problem where we're interested in this function x sine of xy. We're integrating it over the rectangle where x ranges from 0 to 1 and y ranges from negative pi to pi. And I've got the suggestion here that it's much easier to do it in the order dy dx than it is in the order dx dy. So to sort of see what this looks like, we think of integrating first in x on the outside, then in y on the inside, what their range is. We've got our function x sine of xy dy dx. And so as we carry out this integral, since we're first integrating in y, we can treat x as a constant, sort of within the interior here. And so our sine of xy is going to integrate to negative cosine of xy over x, as if we'd done a u substitution where u was xy. And the 1 over x that we get from the argument xy is going to cancel with the x that we had multiplying things out in the beginning. And so we wind up with just a factor of cosine xy, times x over x. Goodness. So that x over x goes to 1. We're evaluating this for y between minus pi and pi. And the result of that is what's going to be our new integrand, depending only on x, that we're going to integrate from 0 to 1 in x. But if we think about it, if we carry this out, we get minus cosine of pi x minus negative cosine of minus pi x, all integrated dx. And from here, we can sort of take advantage of the fact that cosine is an even function, that cosine of negative something is going to be equal to cosine of positive that the sign of the argument doesn't matter. So here we've got minus cosine of pi x plus something equal to cosine of pi x. And so actually this whole integrand goes to 0 everywhere. We're talking about the integral 0 to 1 of 0 dx, which is better known as this constant 0. And so we've got, a value of 0 if we go across this whole area that we cancel out between the positive and negative parts. Just to sort of see what would happen in this if we were to take the alternative, let me do it in blue. If we were to think about the integral, switching the order, so integrating in y on the outside, x on the inside, x sine of xy, dx dy. Here we've got sort of the product of these two functions, x and sine xy. They're both depending on the variable of integration on the inside here. And so we would want to approach this with something like an integration by parts. And if we were to do that, what we'll wind up with, by carrying out this integration by parts, is going to be, and I'm not going to write the sort of intermediate steps here because it's a little bit gnarly and there's not too much space. But we wind up with an integral where we've got from the sort of uv, the boundary terms, we get a sine y over y squared, and from the integral of what is it, v du, the integral term of the integration by parts is going to be a cosine y over y dy. And it's much harder to see that this is going to be equal to 0 as well. We can't use the trigonometric identities as easily. What winds up working is doing a second integration by parts on this first term, where we're taking the derivative of the sine and the antiderivative of the 1 over y squared, and we'll get a cosine y over y term to the positive, as well as a term which clearly vanishes, that we're evaluating sine at pi and minus pi is going to vanish. And so we just, whatever cosine y over y is going to be something that has to cancel out. So it's much much harder to think about that ordering of variables. Alright, so that was just sort of a simple domain. If we think more generally, we're usually going to be relying on these results where we're going to try to decompose our domain that we're trying to integrate over into these parts that are, well, simple. We call vertically simple or horizontally simple, where we know that we've got these functions of y in terms of x or x in terms of y that are sort of giving the extreme extents of the variable on the inside. And so here we're going to want to sort of try to picture our regions, and it's very helpful to draw them in such a way that we can sort of pick out a situation where we've got this behavior where we've just got one interval and then there's a pair of functions that we can compute, and we would like them to be continuous, although sometimes we have to do a sort of piecewise definition and break the integral into several different components. And so here we're going to wind up with a sort of multi-part problem where first we've got to just describe the bounds of integration of the domain, and then carrying it out might also require some degree of effort. depending on which variable, what the ordering is again. And so for a problem relying on this, we've got an integration over some region that's in the first quadrant. So we've got bounds at x equals 0, bounds at y equals 0, and also bounds of this curve y equals 1 minus x squared, and we're trying to compute the integral of this polynomial, x cubed minus 2xy. So here, let me sketch the region a little bit. We know we're in the first quadrant, and we've got 1 minus y equals 1 minus x squared is going to be this parabola that intersects up here at the point 0, 1, and down here, if we look at it, it's going to be at the point 1, 0. It's going to be where we're meeting the two other, sorry about that, we're meeting the two other bounds of the integration in the quadrant. Let's see. Try one more time to get this sized correctly. So we draw out the curve, we can compute the points of intersection between the different parts of the boundary, and that'll allow us to construct the bounds in x and y and relate the two to each other. And so here, we could do either direction of considering it vertically simple or considering it horizontally simple, because we're always going to be between the appropriate axis and the curve, that there's no sort of corners where we're changing the equations defining the boundary. Here it's going to be a little bit easier to consider it with y as the function on the inside, because then we're going to have bounds that are polynomial in x, whereas if we were to solve this for x in terms of y, we would be dealing with a square root, and it should still be doable, but it'll be more difficult. And so here we want to think of doing our integration first in x, and so the smallest that x is 0. Thinking of starting, at the origin or along the y-axis, and x ranges out to 1. And since we're integrating over it first, we're not incorporating any information about the about y yet. We're just saying the extent of x is between 0 and 1. And then once we've got, we think about picking a particular value of x and setting it. We want to get the y bounds in terms of whichever x slice we're at, and so we can think of sort of just a general, we have some value of x and we want to know what's the upper and lower extent of y. We know that we're always starting at the bottom on the x-axis, y equals 0, and the top is just this curve, y equals 1 minus x squared. Our function is as it was given. Here we are doing our integral in y on the inside and x on the outside, and we can start integrating. We can do these integrals now. So here, we first do the interior one. We've got considering it as an integral in y, x cubed is just a constant, and so we're going to wind up with x cubed y. And then 2xy is a linear function of y, and so we're going to get minus xy squared there. And we're going to be evaluating this from y equals 0 to y equals 1 minus x squared dx. And so here we're going to get the integral, let me make that a little bit bigger, from 0 to 1 of x cubed minus x to the 5th from the first term, and then minus x times, and here I'll just expand it out within some parentheses here, 1 minus 2x squared plus x to the 4th dx. And we can collect some of these terms, and so we're going to wind up with a two x to the 5th terms to the negative. We're going to wind up with 3 x cubed terms, and we're going to wind up with 1 negative x term dx. And here, this is going to be a single valued integral, and so we get minus 2 6, so minus 1/3. That's hard to see. Minus 1/3 x to the 6th plus 3/4 x to the 4th minus 1/2 x squared. Doing this from 0 to 1. And did I get the signs correct on this? I believe so. Yeah. And so we plug in 0, we plug in 1, we collect terms together. We're going to get oh, yeah, that's what I put in my notes preparing for this. Putting everything over the 12 to make them comparable, right? We get done this in the wrong order. We get a minus 4/12, a plus 9/12, and a minus 6/12. From the ones, the 0 terms all go to 0, and so this final value is minus 1/12. And to sort of think about, does this make sense? It's interesting to think through. If we look at our integrand, the 0 level set, so where it's switching between positive and negative, is exactly this curve x cubed equals 2xy, or rather x squared is equal to 2y. And to just sort of very roughly sketch that out, it's a parabola passing through the origin instead, and the sort of larger upper bit is the negative one, that if we think about y being positive and x being small, we're going to get these negative values, and then I guess we also have 0 level along the y-axis. But if x is small and non-zero, then we get negative, and if we're over here, we get positive. And so in the region that we care about, there's a lot more to the negative, and also it gets more negative. So it's sort of, it's always good to sort of check to see, does the sign of my answer make sense, that it's a negative answer. And here, I think this sketch sort of shows that it's a reasonable enough thing. Alright, so let's see, that was a first and sort of very straightforward computation. Here we've got something a little bit more, a little bit stranger, that our region is described somewhat more abstractly, that we know we've got these bound y equals 1/4 is going to be the sort of lower bound of our region, but the upper bound is given by, oh, there's a typo here, that this should say x to the 1/2 plus y to the 1/2 equals 1. And so we've sort of implicitly defined this region in the same way that we would say, like, bounds by the circle x squared plus y squared equals 1, or some other equation that's just implicitly defining a curve. And so these can be slightly different to work with, but overall it's very much the same order of steps, is to first think through what does the region look like, and I find it almost always a good idea to sketch this. And so here our two bounds are this line of constant y and this x to the 1/2 plus y to the 1/2 equals 1. And it might not be immediately obvious what this looks like, but either, at great need by hand, plugging in a few values and seeing what it looks like, or using some sort of graphing calculator computational tool, if that's available, allowed. We can see that it's this sort of star-shaped thing where we're around the origin, but bending inwards rather than the circle, bends outwards. But it's the same kind of shape, and the region that we're interested in is this highlighter will not work. So I'll just, is this bit up here. And so we see that the curve is giving us this upper bound, and if we look at the equation, we can think about, what's the largest that we could make, y, and satisfy this. And because you've got these absolute values and stuff going on, we can see that our upper point is going to be 0, 1. That the square root of 1 is 1, and so that's going to be our sort of top point. We're also interested in what these intersection points are, where we're switching, where the two boundary curves meet. And so here we're interested in thinking about what does this equation look like when we know we're at y equals 1/4. And so if we think about this, we've got whatever value of x's that are in this intersection, that x to the 1/2 plus absolute value of 1/4 to the 1/2 equals 1 to the 1/2. And we know what the absolute value of 1/4 to the 1/2 is. It's the square root of a quarter is going to be 1/2. So this equation is absolute value of x to the 1/2 plus 1/2 equals 1, or subtracting over to the other side is equals 1/2. And so here, this is satisfied when x, if we square both sides and then recognize that it's the absolute value, is sort of suppressing the sign, is that we see that this can happen when x is plus or minus 1/4 as well. And so our point of intersection is going to be minus 1/4. 1/4 is the intersection for small x, and positive 1/4, 1/4 is the intersection for larger x. We'll see if we can get this piece. So once we have this, we can write down bounds of our integration, and here there's this excellent question of should we do an integral first with respect to y, then respect to x, or x then y. And we can see that if we were going first with respect to x, we would have to switch from the sort of ascending left cone of this star shape for negative x as our upper boundary, and then switch the function to the sort of the right-hand descending cone. So switching from that red segment of curve to that black segment of curve, and so that we would have to write two pieces of the integral. However, if we're first fixing the value of y, always the red curve is our lower x boundary, our small x boundary, and the black curve is our large x boundary, and we don't have any points where we change between them. And so it's going to be easier here to do an integral with respect to y first. And so that's going to look like y ranging from 1/4 is the smallest value that y takes on, up to 1 is the largest value that y takes on in the region that we care about. And then x is going to be from the red curve to the black curve. So we want to figure out what those two are. And here we know that if we've got a fixed value of y, that we can solve our defining equation for x in terms of that y. And just like we did for the sort of extreme value of y at 1/4, we're going to get the two bounds from the absolute value. Before we were dealing with a specific value of y, 1/4, and we were able to solve it. We can do exactly the same thing, taking 1 minus whatever y to the 1/2 is, squaring it, and then taking both the positive and negative ones, and of course the negative one is going to be that red lower boundary that we have. The positive one is going to be the black upper boundary in this picture. And so here we're going to get what looks perhaps vaguely intimidating, is the integral from 1 minus absolute value of y to the 1/2 squared to positive 1 minus absolute value of y 1/2 all squared. And let me clean up this. 1 minus. And here, since we're looking just for the area of the region, our integrand is just 1, that we're doing the integral across the region just of the differential area. And so once we've got our bounds, then we want to do just this area element dy dx. So here, let me clear out some space here. That'll work. And just let me to have it written down, that's going to give us area. Integrating the differential area across the full region gives the area of the region. And so here, our first integral is just the integral of 1, which just gives the value of y. And so our integral is from x at 1 quarter. Try to write this legibly. X at 1 quarter to x at 1. It's not much better. We're going to get this upper bound minus the lower bound, but since the lower bound is just the negative of the upper bound, we're going to get minus a negative. And so that's going to give us just an overall factor of 2 times this thing in the middle, 1 minus y, 1/2 squared. Oh, goodness, I wrote the wrong order here. Sorry about that. This first integral on the inside is the integral with respect to x, and it's with respect to y on the outside, because we were doing y first. It's the sort of outer integral, and so this should be a dy at the end. And so this we can expand 1/4 to 1, that are 2. Actually, let me pull that 2 in. So we've got 2 minus 4 times y to the 1/2 absolute value, plus 2 times y to the 1/2 squared, or just, absolute value of y, dy. Clear that away. And here we can rely on the fact that in the region we're talking about, between y equals 1/4 and y equals 1, we know that y is positive, and so that's going to tell us that in this region here, the absolute value of y is just equal to y, that we know we're in this positive region. And so our integral, I guess the first one is going to be fine, is going to be 2, is just going to integrate to 2y. But then our next term is we just have to think about taking the antiderivative of y to the 1/2, rather than worrying about what does this absolute value do to the antiderivative. That we know which case we're in, and it's only the one case. And so here, our y to the 1/2 is going to be a y to the 3/2 times 2/3. So we're going to get minus 8/3 y to the 3/2. And our absolute value of y is going to be equal to 2y, and so that's going to just integrate to y squared. It's between 1/4 and 1. And with this last bit here, we're going to have a little bit more trouble than usual because we don't have a boundary at 0. We've got this 1/4. But we can see that as we put these things in, we get 2 minus 8/3 plus a half, and then we're going to get minus 2/4, so minus 1/2. We're going to get minus a negative. If we take 1/4 to the 3/2 power, the square root brings us down to 1/2. The cube brings us up to 1/8, and so we're going to cancel with this 8 to get 1/3. And then finally we're going to get minus 1/4 squared, which is going to be 1/16. And I'll save the arithmetic here, but we deal with all these things and we get 5/48 as the area of this region. And just as a quick check, it's a positive value for area, which is good, and it's a very small value, but my sketch here is very rough. If you graph it with some kind of software, you can see that the sort of spikes on this star shape get very thin very rapidly, and so even though we're cutting off 3/4 of the height of this spike, it's a very thin one, so it is not entirely unreasonable. Alright. The last problem on this sort of idea of just like how do we deal with the general domains is a little bit different, is worrying just about what this region looks like. And so here, rather than giving our geometric description of the region and trying to figure out bounds with regards to it, our sort of task is to take the bounds of this integral, where it doesn't matter what the function is, just what the bounds are, and to sort of reconstruct what this region has to be and use that to produce the other ordering of the variables, doing the integral of y first then x, or y on the outside then x on the inside, rather than y on the inside, x on the outside. And so what we want to be thinking about here is, first off, that we look at the bounds in x. They're between 1 and 5, so we know we're in the sort of right half space. That if we draw out as part of the xy plane, that we're going to be in, make them larger dashes, this sort of strip between 1 and 5, and then giving further constraints in the strip is we've got these conditions on y, and so we know that the well, we hope to be the upper extreme, and that the integrals aren't flipped, but that we know that one of our extremes is given by this equation y equals 11 minus x over 2, and what we hope to be the lower extreme is given by this equation y equals x minus 2. And so here, if we plot out those curves, I I fear my proportions are a little bit skewed here, but we're going to get one curve of positive slope 1, that's going to give us sort of our lower bound, and we're going to get a curve of slope negative 1/2 that's going to give us an upper bound for the region. And so we're going to say that our x equals 1, we can see that that's going to give one bound, and then if we trust this sketch, we're going to get one lower bound from y equals x minus 2, and one upper bound from y equals 11 minus x over 2. And so D is going to wind up being this triangle. Now, if you're like me, your sketches are not always entirely accurate, at least without doing some sort of algebra to check where the where things are intersecting and whatnot. And so it's worthwhile thinking through that, like, with the equations that we have access to, and it'll turn out that x equals 5 will just sort of fall out. We want to know, like, where these intersections occur, and so if we can say that we want to know, first, where does that intersection go? We want to just do y equals 11 minus 1 over 2. And so we can see that there's one point of intersection at, let's bring that closer, over 2, at 1, 5 is coming from that first, where do those two curves intersect? Similarly, we can ask, where do these two curves intersect, x equals 1 and y equals x minus 2? That's going to be at a point given by 1 and negative 1. And finally, we can ask, where do those two curves intersect? And that's going to be where 11 minus x over 2 is equal to x minus 2, and that happens when, if we solve for x, that's going to be, it's going to be x, but is going to happen at 5. And so because we know that we've got this intersection occurring at this, other extreme of x we have, we can be sort of like assured that they do meet, and they've got a triangle and not like a trapezoid that we might have wound up with if they weren't lined up correctly. But they meet at 5, and then if you substitute 5 into either equation, we get out 3. And so ultimately what we get is that D is the triangle with vertices vertices 1, 5, 1, negative 1, and 5, 3. And we can be sure it's a triangle because our equations in y are linear, that we've got straight lines defining it, and there could have been 4 points of intersection between the 2 choices for a y-bound and the 2 choices for an x-bound, but 2 of them agree, and so there's only 3 points of intersection. So we've got a thing with straight lines connecting 3 points, so it's a triangle. So now that we have that, we can think about, all right, with this triangle, what's our integral in terms of dx dy, or sort of in terms of integrating over y first. And here we're going to see that at this critical value of y equals 3, we're going to be switching from the curve y equals x minus 2, which is giving us our sort of lower boundary, to this curve y equals 11 minus x over 2. That's sort of upper boundary. And so we're going to need two different terms, because we've got a sort of like piecewise defined right bound. And so we can think the first integration in y, that's got a simple thing, a simple region is going to be from y ranging from -1 up to 3. And in this range, we've got x ranging from 1 on the left all the way up to the point satisfying y equals x minus 2, which we can solve for x as being x equals y plus 2, or I guess 2 plus y. And then we've just got the same f of x y dx dy, integration of x in the middle, but we need to add in an extra term that's accounting for the rest of it, where y is ranging from 3 all the way up to the maximum of y is at 5. And here x is ranging again from 1 on the left, but now we're using the other boundary, the sort of upper line. And so here we need to solve this one for x. We're going to get x is 11 minus 2y. And again, just f of xy dx dy. And so this is sort of a situation where, like, if we knew about this region, we could think, oh, is it going to be easier to switch the order of integration? But the answer in this case is probably no, unless somehow the function of f is much easier to integrate x first, or to integrate with these choices of 2 plus y and 11 minus 2y involved, rather than the bounds on x. But the sort of generic answer for the region is just what makes the compact expression for the integral the original order dy dx. You only need the one region. It's simple the whole way along, rather than having these two parts. All right. So that brings up the last sort of thing that I want to talk about on this section, which is this sort of interpretation that gives rise to a bunch of these double integrals. And that's with talking about the volume of some solid three-dimensional object, where we know that it's lying between two surfaces that are over the same region. And so here we've got these two functions, that's that sort of upper boundary and the lower boundary, f and g, that are defining the height of these two surfaces, and then our integral, our double integral of the difference in height across this whole area is going to give us the volume that we're sort of summing up the little very thin rectangles, or very thin prisms, that are the sort of well, not cross sections, the bits of volume that are sort of over a particular point in this D region that is sort of intersecting our shape, or lying below the shape, or above it or something, but indexing our shape. And so for what that looks like, is we might say that we've got some surface that's defined by, like, say, cosine x, cosine y. It's giving it a sort of upper bound, or an upper surface, although it's worth checking that it's it's greater than the other one, and sine x, sine y giving the lower surface. And we need to know that, like, we're interested in the surface that's sort of over a particular set. And so here, that set is this triangle defined by the origin and these 2 points, pi over 2, 0, and 0, pi over 2. And so the idea is that in the xy plane, this is the sort of shadow of our shape, and it's lying over it. I think I will not attempt to draw this in 3 dimensions because it will get very confusing to draw. Other surfaces might be easier to draw, and it's almost always a good idea to attempt. This one is not particularly amenable to illustration. But we can check, just to be sure, that, is cosine x, cosine y the, like, upper bound? Like, do we have this inequality between the two? And if we do that, we kind of want to just think about, actually, let me put this up here. To sort of make sure that it's not going to take up space that we need later. And so if we look at the difference, cosine x, cosine y minus sine x, sine y, and we sort of want this to be a sort of positive thing for cosine x, cosine y to be bigger than sine x, sine y. If we look at it, it looks perhaps like a thing that has a trigonometric identity true about it, and consulting your favorite source of trigonometric identities, or if you're fortunate enough to remember this one, is we've got cosine x, cosine y minus sine x, sine y is going to be product to sum formula. This is going to be cosine of x plus y. And so if we're in this triangle where our x and our y, they're both positive, and they're sort of one of these boundary lines, if we think about what this line is the line x plus y. Well, the line, I guess, is going to be x plus y equals pi over 2. Is that cosine of x plus y, if we know that x plus y is non-negative, because x and y are both non-negative, and it's at most pi over 2, we know that the cosine is going to be non-negative as well. And so we know that in this whole region, cosine x, cosine y is going to be greater than or equal to sine x, sine y, that we know that inequality there. And so we've correctly identified the upper and the lower bounds. We haven't created a self-intersecting surface. It's always good to check these kinds of things. But alright, so once we have this, the integral that we want to set up is going to be just a double integral over this triangle. And so here it's pretty symmetric, so the order doesn't matter too much, that we've got just 0 to pi over 2 is going to be our range. let me consult my notes to make sure I don't get sign errors. Yeah, if we think about that as the integral in x first, here as well, then we can say that the y, because our relationship is the sum equals pi over 2, the upper bound on y is going to be pi over 2 minus whatever value of x we had, and then our integrand is going to be the difference between the upper height and the lower height, and so it's going to be exactly this: cosine x cosine y minus sine x sine y dy dx. Move that up so that it's not in the way as much. Dy dx. And of course we could use the same identity here, up here, replacing this integrand with cosine of x plus y. And it would probably make things fairly nice, but even without that, it's still not too bad. That our integral is 0 to pi over 2. If we take this antiderivative in y, cosine is going to go up to sine, so we get cosine x sine y. Sine is going to go to negative cosine, and we had a negative sign out here, so we're going to get sine x cosine y from 0 to pi over 2. In y, this whole thing is still integrated dx. And so here, we're going to want to use another trigonometric identity here, which is this, that sine of pi over 2 minus x, which is going to be a thing that we get. Yeah, that is what the upper bound is. It's gonna, it's the thing that we're going to be substituting in as the upper bound is just cosine of x, and similarly cosine of pi over 2 minus x is sine of x. And like if you sort of draw them out and shift them around appropriately, you can convince yourself of that. And so what we're going to get is, doing this evaluation, if we do plug in to sine of y, pi over 2 minus x, we're going to get cosine of x in red. So we're going to get a cosine squared of x from the upper bound on sine of y. From the lower bound, plugging in y equals 0, we've got sine of 0 is 0, so that doesn't contribute. Then over here, from the pi over 2 minus x is going to turn the cosine y into a sine x, and so we're going to get a sine squared of x. And here, cosine of 0 is 1, and so the lower bound is going to contribute a minus 1 dx. Or, sorry, not a minus 1. Is going to contribute minus 1 times sine of x. Dx. And so, of course, cosine squared plus sine squared of x, the sort of most important trigonometric identity of all of them, is that equals 1. And so when we take our antiderivative here, we're going to be integrating 1, which will go up to x, and then minus sine of x will go to cosine of x. This is from 0 to pi over 2. And so we're going to get a pi over 2 from the x minus 0 plus cosine of pi over 2, which is 0, minus cosine of 0, which is 1. And so our final answer is the sort of strange looking pi over 2 minus 1. It's a bit weird to mix integers and multiples of pi, but that's what we get here. And so this is the sort of volume of this rather weird. It's going to be, you know, if you do get a 3D plotting software, it's like this like wavy thing over a triangle. It's very strange that it's you know, got like a hollowed out bit in the bottom as well as a curve in the top, and they come to meet each other on the edge of it. So it's a funky looking region. It kind of makes sense that it's got a funky looking volume. Alright, and that is the last of the slides that I wanted to get through, so I will leave this section here.